Welcome to the Explainer. Today, I want you to imagine we're setting up a virtual laboratory experiment. We aren't just going to look at one single machine learning model in isolation. No way. Instead, we're going to run a massive head-to-head competition right inside Python. We'll literally be comparing the performance of 14 different machine learning algorithms simultaneously. It's an absolutely fantastic way to see exactly how different classifiers behave on the exact same dataset, and I am super thrilled to guide you through this whole setup step by step.
Okay, let's dive into this. Here's our chronological journey for today. We'll start with generating synthetic data, move on to the 80-20 data split, then training 14 ML models, visualizing model performance, and finally, building your data portfolio. Think of this as our exact developer roadmap. It shows exactly how our Jupyter Notebook experiment is going to flow from start to finish. Step 1, we generate. Step 2, we split. Step 3, we train, and Step 4, we visualize. It's a clean, super logical pipeline that actually forms the backbone of countless data science projects out there.
Section 1. Generating synthetic data. Let's gather the raw materials for our lab experiment. So, instead of scraping messy, unpredictable real-world events, we're going to generate completely clean test data. We do this using a brilliant little function called make_classification, which comes straight out of scikit-learn. This handy function basically assigns our newly generated synthetic data directly to our x and y variables. Let's take a peek at the specific parameters we pass into that function. Our code specifies n samples equals 1,000. That simply means we're generating exactly 1,000 data points, or rows, for our algorithms to learn from. Right alongside that, we specify n features equals 5, giving us 5 input columns, and n classes equals 2, meaning the models will try to sort all this data into 2 distinct categories. Oh, and we also set redundant features to 0 and fix our random state to 1. Why? Just to ensure our experiment has perfect stability and is totally reproducible.
Moving right along to Section 2, the 80-20 data split. This is our crucial prep phase.
Now, what's really interesting here is just how much heavy lifting a single Python library can do for us. Seriously, scikit-learn is an absolute powerhouse. From it, we're importing the train-test-split function to cleanly chop our variables into the exact groups we need.
By setting our test size parameter to 0.2, we instantly divide up those 1,000 samples. 800 of those samples form our training control group, the data our models will actually learn from. Meanwhile, the remaining 200 samples are held back for the final test. The end result? We can currently generate xtrain, xtest, ytrain, and ytest all in one go.
Section 3. Training 14 ML models. It's time for model building, the part where we let the computer completely take over.
Just think about the sheer power of the script we're running right now. We aren't just testing one model. We are iterating through 14 different machine learning algorithms simultaneously. We store their names in a simple list and then use a for loop to construct the models one by one. And for today's experiment, we're just using the basic default hyperparameters for every single algorithm. It's honestly the perfect way to establish a solid baseline before you even start worrying about automated optimization down the line.
So, the model building process runs its course. It loops over those 14 algorithms, making predictions using that held-back x_test data we saved earlier, and it calculates an accuracy score for each one. When it finishes, it spits out accuracy scores ranging from 0.79 all the way up to 0.885. But here's the catch. It just appends these to a variable simply called scores. This gives us a plain, pretty boring list of raw numbers. I mean, it's highly informative, sure, but it's kind of tough to look at. It desperately needs a major upgrade.
Which brings us to Section 4. Visualizing model performance. This is the aesthetic payoff. We're going to take those plain numbers and spice them up using pandas and seaborn.
And this brilliantly illustrates the difference a good visual makes. We take our empty pandas data frame, feed it the names of our 14 models along with their corresponding scores, and then apply a seaborn background gradient style. Just look at how the color coding works. The models with the lowest performance are automatically highlighted with a lighter shade of green, while the absolute best performing models get a dark, rich shade of green. You instantly know exactly where to look.
But we don't have to stop at a table. Using Seaborn, we can create a really crisp, clean bar plot. We map the names of the algorithms right onto the y-axis, the accuracy scores onto the x-axis, and we set a stark white background for ultimate readability. This visual transformation takes the exact same data from our data frame and lets you compare the varying success of all 14 classifiers in a fraction of a second. It's just a massive, massive improvement over a text list.
Section 5. Building your data portfolio. Now let's zoom out from the code for a second and talk about the big picture. Why running this specific experiment matters so much for an aspiring data scientist.
As a focused learner, you shouldn't just passively watch this explainer. You should absolutely actively participate. Take this framework and play around with the code yourself. Try modifying the input data. What do you think happens to the models if you change those 1,000 samples to 10,000? Try it out. And once you make those tweaks, upload your own unique version to a GitHub repository. Every single time you do this, your data science portfolio grows stronger.
I really want to leave you with this incredibly empowering piece of advice directly from our source material. The best way to learn data science is to do data science and to build your data science portfolio. It hits the nail on the head, right? You don't learn just by reading about it, you learn by experimenting, running loops, breaking things, and visualizing the outcomes.
So the framework is set. You now have the exact code to generate, split, train, and visualize. My final question to you is this. Which dataset will you test these 14 algorithms on next? I highly encourage you to open up your command prompt right now, launch Jupyter Notebook, and find out. Thanks so much for joining me on this explainer, and happy coding.